Well, today we're going to talk about angular momentum. And angular momentum is another case of momentum, and it is the moment of the momentum about a point or an axis. So let's review what moment is from statics. If we have a force acting through a distance, we know that the moment about O is force times distance. We also know that only the component of the force that is perpendicular to the distance counts for that moment, such that we have a cosine component times that distance is actually what the moment about O is. All right, in dynamics we have a similar situation. We're going to call angular momentum the capital letter H, and we're going to say it is the momentum, the mv, times that distance from the point of reference or the point of rotation, so that H is equal to momentum, mv, times d, and only the component of the momentum that is perpendicular to the distance from the reference point counts, such that if you had a velocity in both the y direction and the x direction, it is only the y direction, because y is perpendicular to d, only the y direction counts. So I'd say that it is the momentum, the mv in the y direction, times d is equal to the angular momentum about point O. Also, just to note that angular momentum needs a reference point, such that the angular momentum about point O, which is going to be mv y times d, is going to be different than the angular momentum about some other point, about A. So clearly the reference point is the lever arm. That is important, that you need to keep track of. All right? All right, so angular momentum can be changed by angular impulse. So in this case we have angular momentum and m times v, and the momentum mv times d. And if I apply a force through a time and through a distance, I can change that angular momentum, and that's probably easy to see. And we're going to call that our momentum equation, such that h1, condition 1, plus the integral of m dt is equal to h2, where m is the force times the distance. So the moment would be force times distance. In our momentum we have to have a time, or in our impulse we have to have a time involved. So we're going to say that the force times distance acting through a particular time changes my mv times d. All right, so that's pretty easy to see. And again, only the component that is perpendicular to the lever arm makes a difference. In other words, if I had a force in the x direction, that doesn't help give me angular momentum. Even if it is changing d, it still doesn't count. Only the components of force perpendicular to the d, only the components of mv perpendicular to d count as angular momentum. All right, so that if we had a beginning angular momentum, then we'll have the integral of f y times d dt is equal to angular momentum condition 2. All right, we're going to do some problems like that to help you understand that. Then also the angular impulse can be applied, from applied forces like I have here, or it can be from an applied moment, a torque or something about that shaft. So we could have a force times distance times the time, right there. Or we could have, or in addition to, we could have a moment, a torque, times a time. So the sum of the moment times time, in this case, if I call this my positive direction, I'd have a positive moment times dt minus the force times distance, dt would be equal to h2. All right? So we have to pick a direction. As positive, momentum is a direction, or is a vector. Angular momentum is a vector as well. The direction matters, obviously, as well as the magnitude. So a positive direction, counterclockwise, is conventional as positive direction. Okay, so here's a couple pictures. This particular problem is very easy, but in this case we have a mass out at the end of a shaft, a rod. It's moving in that direction. We're going to apply a 5 Newton force to it for a particular time, and over another period of time, or through that time, then the angular momentum is changed. So again, when the radius is constant or the lever arm is constant, it's fairly easy. In this one, note that we have an angle, force at an angle, but only the cosine component, only this component is going to add to the angular momentum. The sine component, which would be in this direction, be that piece of it in that direction, is not going to add to the angular momentum, and neither will that force over here. So the only force contributing to the impulse which would add to angular momentum would be the cosine component. Same with this guy. This one has a rotating about the shaft. We got this weight out here at the end, and we got a moment kind of twisting it in this direction, so it looks like we may have to integrate that one because it's a function of time. But again, only the component that is perpendicular to the direction counts for angular momentum. So it would only be this 3/5 component acting in this direction. That would be the piece of it, that piece of that applied force that would contribute to the impulse. Here's another shaft being twisted by a torque. So, all right, you'll notice that all of these are in the horizontal plane, if you will. This is horizontal. We're looking straight down on it. We're looking straight down on that one. This is rotating in the horizontal plane, and so is this one. Well, the horizontal plane is helpful, and it's important to know which plane you're in, such that if you were to look at these two problems in the vertical plane, it may not work quite right. In other words, if it's balanced in the vertical plane, then the like this shaft here with the 4 weights on there that are all balanced, or like a bicycle wheel or something like that, then you can work angular momentum properly in the vertical plane. However, when you have something out of balance like this, it doesn't work properly in the vertical plane because the mass of this and the weight will be lopsided, and it won't be a smooth motion. Okay. All right, let's do an easy problem here, and we'll just work through a couple simple ones. But this is the picture that I just had before. So we're going to say that it's a 5 kilogram block, starts with a speed of 2 meters per second. We're going to have a tangential force here of 5 newtons, and we're going to act through a period of 3 seconds, and we want to find out the velocity at the end of 3 seconds. So beginning momentum plus the integral of m dt is equal to ending momentum, and the momentum again is the mass times velocity times the distance, or mvr. The ending angular momentum will be mv times its r, and the impulse we're going to have is the force times the distance times the time, and multiply all those out. And because r is constant, I put them all into the equation, but r is constant in this situation, so that the ending velocity is 5 meters per second. All right, this one we were just looking at. We'll have to do just a little bit of integration, so let's do that together. So I'm going to say that in this case it's got one mass out here at the end. It has a mass of 10 kilograms attached to the end of the rod. It's got a couple, this moment right here, and then this 3/5 component, which we already talked about. We said that to determine the speed when the cylinder is at time is equal to 2 seconds, and it has an initial speed of 2 meters per second. So let's say that h1 plus the sum of the integral of m dt is equal to h2, and h1 would be mvr plus, and then we have that moment, we'll talk about that, the integral of 8t squared plus 5 dt, plus, that one's also going in here, we'll have that 3/5 component, so 3/5 of 60 times the distance that it moves, which is, or the lever arm would be 0.75, and then the time is 2 seconds. I guess I better put it over here. We're going to integrate this from 0 to 2, and then we're going to equal our mvr condition 2. All right, plugging in all the numbers here, we have a mass of 10 kilograms, so 10 kilograms. The velocity here beginning is, I believe it was 2 meters per second. My radius is 0.75. Integrating that, I have plus 8t cubed over 3 plus 5t, and that piece needs to be evaluated from 0 to 2. And I get that all multiplied out, 3/5. Guess I didn't multiply it out on my work paper here, so I'll just write it all out here. 0.75 times 2 is equal to my mass of 10 times V2 is my unknown that I'm looking for, and R was 0.75, and I get V2 is equal to 13.37 meters per second. All right, so that one's fairly simple.